Okay, here we go. So we're in the middle of our Polygon unit. Started it yesterday. Yesterday you got the basic information about polygons, how we name polygons, what the various names are for the polygons with 3 sides up to 12 sides, how to name a polygon with more than 12 sides. Excuse me. You also learned the difference between equilateral, equiangular, and regular. Remember, regular is both equilateral and equiangular. We're going to be seeing that term come up some more today, regular. You also looked at convex and concave, etc. But basically, we were talking about the general information with polygons and those shapes that these segments create when they're connected end to end. Today we're going to be looking at angles specifically. We're going to look at interior angles in polygons, and we're going to look at exterior angles in polygons. Interior, of course, meaning inside, and exterior meaning outside. So we're going to start with interior angles and go through the different types that we get there. And then we'll look at exterior angles at the end. All in all, there are going to be 3 different formulas that you're going to have to be able to use, or formulas or theorems that you're going to have to be able to use, some of which you will have to have memorized because they are more highly useful than others will be, and that will come in more useful in terms of proofwriting later on in the year. All right, so we start with our interior angles of a polygon. There isn't a formal definition here on this first one. It's just a matter of defining what we mean by interior angles. So let's start with a polygon. Now, of course, interior means it's simply inside. So here the interior angles would be here and there. And these don't all have to be the same size. They could be different sizes. Some of them could be the same, but they don't have to be. It kind of looks like in the one that I've drawn that they would be equal. But because I don't know those measures specifically, I'm going to mark them all differently to indicate that they could be all different angles. What we're going to be looking at is, how do I figure out in a polygon the total of those angles that I've marked? So here in this pentagon, how much or what sum should I get when I add those 5 measures together? Likewise, what if I'm given 4 of those measures and I need to find the 5th one? How do I do that? That's what we're looking for in these formulas today. So ultimately what we're looking at with interiors is, what is the sum of the angles on the interior of the polygon? And secondly, if I'm given information, how do I find what's missing using that sum of those measures? Okay, so we're going to look first at the triangle sum theorem. This thing's a little jerky again today. The triangle sum theorem, you'll notice, has little stars next to it. Remember what that means. That's one of those things that we need to add to our vocab cards and memorize. So, as we've done previously, go ahead and highlight that in some form. But the triangle sum theorem simply says the sum of the measures and there's that sum word again. The sum of the measures of the interior angles of a triangle is 180 degrees. The sum of the measures of the interior angles of a triangle is 180 degrees. So in this case, we're going to start with some random triangle, and I'm going to name it ABC. Doesn't matter what kind of triangle you draw, just any old triangle will do. Label one vertex A, one vertex B, and one vertex C. And according to the triangle sum theorem, if I take the measure of angle A, whatever it happens to be, plus the measure of angle B, plus the measure of angle C, then I will get 180 degrees. Now, if I'm given two of them, I can find the third. Fill them in the appropriate places in my equation, and then solve for whatever's unknown. But ultimately, the three angle measures should total 180 degrees. So we have three examples down here below that we're going to be looking at. Use the triangle sum theorem to answer the following questions. In triangle ABC, the measure of angle A is 90 degrees and the measure of angle B is 35 degrees. Find the measure of angle C. So according to the triangle sum theorem, since it's triangle ABC here, the measure of angle A plus the measure of angle B plus the measure of angle C should equal 180 degrees. Now I'm going to substitute the values that I'm given into the appropriate places in that equation and then solve for what's unknown. So in place of the measure of angle A, we have 90 degrees. The measure of angle B, we're told, is 35 degrees. And the measure of angle C, that's our unknown, so we're going to leave that as it is for now. And now we have an equation that we can simply solve by adding and subtracting. Okay, so we're going to combine our like terms here. The 90 plus the 35 gives us 125 degrees, plus the measure of angle C equals 180 degrees. And now we need to subtract that 125 from both sides, so the measure of angle C, will be 55 degrees. Now you can check these. If you go off to the side and add those three angle measures together, 90, 35, and 55, if I add those together, it should be 180. So I carry my 1, 10, and 3 and 5 make 18. So that checked out appropriately, which means I know this is the right answer. And that's the lovely thing about all of these today. There is some way to check yourself to make sure it's correct. So there's no reason to miss any of them. All right, number 2, in triangle DEF, the measure of angle D, whoops, that should be capitalized, is 80 degrees. And the measure of angle E equals the measure of angle F. Find the measure of angles E and F. Okay, so we've got triangle DEF. So that tells us the measure of angle D plus the measure of angle E plus the measure of angle F equals 180 degrees. Substitute in the known values. The measure of angle D is 80 degrees plus the measure of angle E and the measure of angle F are the same. So what that means is I'm going to substitute for one of them but not both. In this case, I'm going to leave the measure of angle E as it is, and in place of the measure of angle F, I'm going to put what it's equal to. So we'll replace that with the measure of angle E, because they are equal. Okay? Don't substitute both of them, because if you substitute both of them, you're going to end up right back where you started, and you'll just end up with the F and the E switched. So combine our like terms like we did on the last one. Here, the 80 drops down, plus the measure of angle E plus the measure of angle E. Think of that like x plus x is 2x, or y plus y is 2y. The measure of angle E plus the measure of angle E is 2 times the measure of angle E. It's just adding those coefficients like what we did when we combined like terms in algebra. Okay, so now we're down to a two-step equation. I want to subtract the 80 from both sides. So 2 times the measure of angle E equals 100 degrees. And then lastly, divide by that 2. So the measure of angle E equals 50 degrees. Keep in mind, the problem asked you to find not only the measure of angle E, but also the measure of angle F. And we know that it is equal to the measure of angle E, so it should also be 50 degrees. Okay, so a quick check to see if we're right. D we were given as 80 degrees. E and F were both 50. So adding those together, we get 180. So that works out just fine, and that tells us our answer is correct. All right, last one of this type, number 3. In triangle GHJ, that's kind of a mouthful, the measure of angle G is 48 degrees, and the measure of angle H is double the measure of angle J. Find the measure of angles H and J. Okay, so with our triangle GHJ, the measure of angle G plus the measure of angle H plus the measure of angle J equals 180 degrees. We're given a measurement for G of 48 degrees, so we'll substitute that in. And now I've got to deal with this second sentence in the problem. The measure of angle H is double the measure of angle J. So we need to kind of literally translate this into a math statement. The measure of angle H, remember how we write that? The measure of angle H is, or equals, double, that means multiply by 2, double the measure of angle J. The measure of angle H is double the measure of angle J. Okay, so what that means here is that in place of H, wherever this appears in my equation, I'm going to substitute in 2 times the measure of angle J. So here, back to our equation, we'll have 2 times the measure of angle J plus the measure of angle J equals 180 degrees. Okay, so we combine our like terms. Remember, this is just like combining your coefficients. 2 of the measure of angle J plus the measure of angle J will leave us with 3 times the measure of angle J out there. We still got this 48 degrees out here at the front, so we'll go ahead and drop that down as well, equals 180 degrees. And now we're back to the same 2 steps we had in the last problem, subtract and divide. So we subtract 48 degrees from both sides first, get 132 degrees over there on the right. Divide by 3, and we get the measure of angle J is 44 degrees. Now if I take that back over here and substitute it in there, I can find the measure of angle H. So the measure of angle H equals 2 times the measure of angle J, which is 44 degrees. So the measure of angle H should be 88 degrees. Double check, make sure we get everything right. 48 plus 44 plus 88. 16 and 4 is 20, carry the 2. 8 and 8 is 16, with the 2 there is 180, so that checked out just fine, and we can be certain that our answers are correct. Now, if you ever did find a problem in your check, simply go back and, first of all, re-add the numbers in your check. Make sure that you've added correctly. Then if that doesn't work out, go back and look at your work and determine where your mistake was at. Maybe it was in the original equation you wrote, maybe it was somewhere else, but double check and find it. All right, so we talked specifically on the first page about triangles. Now we're looking at polygons in general. So we're looking at the Polygon interior angles theorem. And this will work for any other polygon. It works for a 3-sided triangle as well, but the triangle sum theorem takes care of that for us. The triangle sum theorem is actually from this theorem. We'll talk more about that at a later date. But this is what we're going to use for anything with 4 sides, 5 sides, infinitely many sides, whatever it happens to be. You're not going to have to draw anything or work with anything with infinitely many sides. But this works for any other polygon from 3 up. We're going to use it for the ones that have 4 or more sides. Okay, so it starts the same way. The sum of the measures. The sum of the measures of the interior angles just like what the triangle sum theorem said. The sum of the measures of the interior angles of a polygon is 180 degrees times n minus 2. And n is the number of sides. Some might refer to it as the number of vertices, which is the same as the number of sides. But ultimately, we're going to use that formula, 180 degrees equal times n minus 2. That's going to give us the sum of the measures. And remember at the beginning, I said we're looking for two different types of things. We're looking for the sum of the measures, and in some cases, we'll be looking for a missing measurement. So on these first few here, on number 4, we're going to find simply the sum. Find the sum of the measures of the interior angles of each type of polygon. And then we'll be using this formula a little differently in the next few problems after that. So a decagon to begin with. Remember what deca means? Like decade. That tells us n is 10. So we go to our formula. The sum equals 180 degrees times n minus 2. And we're simply going to substitute this 10 in here in place of n. So 180 degrees times 10 minus 2, which we all know to be 8, hopefully. And then we simply multiply. 180 degrees times 8, 1,440 degrees. And that would be the answer then to part A. Okay, moving on to part B, we're looking at, whoops, sorry about that. B is a quadrilateral. Remember what quad indicates, quad meaning 4. So here, n is 4. We'll use our same sum formula. The sum is 180 degrees times n minus 2. And this time we're going to substitute in a 4 in place of n. So 4 minus 2 is 2. Multiply that by 180. And every quadrilateral should have a sum of 360 degrees. And the last one, a heptagon. Remember, a heptagon has 7 sides. So same formula, the sum equals 180 degrees times n minus 2, substituting in a 7. So 7 minus 2 is 5. 5 times 180 gives us 900 degrees. And that, remember, this is just the sum of the values. And these next couple of problems, we're going to be looking at what if I have to go beyond that? What if I need more than just the sum? How do I use that to solve a problem? So we look at number 5. Find the value of x in the diagram. Now, first things first, in the diagram, I see 5 angles. I see 5 sides. That tells me something about n. N is 5. And notice we're given 4 of those measurements and we're asked to find the 5th one, find the value of x. So in this case, I need to first of all determine what is the sum of those measures. So I go back to my sum formula, 180 degrees times n minus 2. Substitute n as 5. And then multiply as we did before. So 5 minus 2 is 3. 3 times 180 is 540 degrees. So that tells us that all 5 angle measures, all 5 of them, should have a sum of 540 degrees. Now I've got 4 of them, so I'm going to figure out what the sum of those 4 is and determine what's left over out of this sum of 540 that we've determined. So we take our 114, 105, 102, and 135 and add those together to determine how many degrees are already used up, so to speak, out of that 540. Okay, so 4 and 5 is 9, plus 2 is 11, plus 5 is 16. 1 and 1 is 2, plus 3 is 5. And then in the hundreds column, 1, 2, 3, 4. So of the 540 degrees, 456 of them are already spoken for. So to determine what's left, take 540 and subtract 456. Borrow 4, borrow again, 13 minus 5 is 8. So we get 84 degrees for that final angle. And there again, you can double check yourself. Add all 5 measurements together and make sure that they total 540 degrees. Number 6. A heptagon has 4 interior angles that measure 160 degrees each, and 2 interior angles that are right angles. What is the measure of the other interior angle? Now, although it's not listed out like one by one, we're given, for our heptagon of 7 sides, we're given 6 of the angles. 4 of them at 160 degrees each, and 2 of them are right angles. And remember, that means they're going to be 90 degrees. Okay, so we have to determine, first of all, with our heptagon, which has 7 sides, we have to determine what the sum of those 7 angles should be. So 180 degrees times n minus 2, 180 degrees times 7 minus 2, which is 5, and 5 times 180 should be 900 degrees. So we know that our total for all 7 has to be 900 degrees. We have 4 of them at 160 each. So 4 at 160 degrees each, let's go ahead and multiply that out and see what that is. Gives us 640 degrees. And we have 2 right angles. So 290 degrees would be 180. So add those 2 results together. 640 plus 180. Carry a 1. And we have 820 degrees already spoken for. So I know I need a total of 900, 820 of which are already taken care of. So we'll go ahead and subtract there to see what's remaining. And the remaining angle in this case should measure 80 degrees. Finding our unknown angle measurements. All right, and number 7, find the measure of each interior angle of a regular 11-gon. Now be very careful of that word regular. Sometimes we tend to kind of glisten over it. You have to read carefully. Remember, regular means a polygon has all congruent sides and all congruent angles. So in this case, we're not asked for a sum, we're asked for the measure of each angle. And if those angles have to be congruent, meaning they have to have the same measure, then I have to know, first of all, how much should they total? And then I can simply divide to determine how much each one of them is. Keep in mind, this only works if the polygon is regular. You have to know that all of the angles are congruent first. So we start with our sum formula. In this case, we're looking at an 11-gon, so n is 11. Let's scroll that up a bit so you can see a little better. Oh well, I'm at the bottom of the page, silly. All right, so the sum is 180 degrees times n minus 2. Substitute in your value of 11. So 9 times 180 gives us 1620. And remember, that's all 11 angles added together. Because the polygon is regular, we know all 11 angles have to have the same measure. So we'll take 1620 and divide it by 11. You're dividing by n to determine the measure of each angle. Now the reason I include this one is not only so that we get an idea of what regular polygons do and that we're carefully watching that, but also because I want to point out something here. As you do the division, you'll find that it doesn't divide out evenly. That you get this long repeating decimal. Angles do not have to be measured in whole units. You can have fractional units for an angle. Now, I could write that as a repeating decimal. If you're going to do that, make sure you include the little bar above the repeating decimals, or places those values. That bar, by the way, is called a vinculum. Kind of a fun word to say if you just kind of let your mouth move around. But anyway, a vinculum, if you want to use that with your repeating decimal, you can. You can write it as a mixed number, as I've done here, 147 and 3/11 degrees. One thing I do not want you to do is round. Do not round. By rounding it, you're slightly changing the value of that angle, and then when I go to check it with your rounded answer, it won't work. Because remember, I should be able to take that value of 147 and 3/11 and multiply it by 11, and it should give me 1,620 as an answer. If you round the answer, when you multiply it, I'm not going to get exactly 1,620 degrees. So don't round because you're affecting the value of the answer by doing so. So either repeating decimals, mixed numbers, but no rounding. Okay, so that takes care of all the interior angle things. We've talked about the interior angles of a triangle, the interior angles of a polygon. What about exterior angles? So an exterior angle is an angle adjacent to, and remember we've talked about adjacent before, adjacent to an interior angle of a polygon. An angle adjacent to an interior angle. Remember what adjacent means. They're neighboring, like you and your neighbor. You share a boundary line between the two properties, but your property never overlaps their property. Same way with our adjacent angles. They're next to each other, they share a side, they share a vertex, but they don't have any interior points in common. The points in the interior of one angle never intersect the points in the interior of the other. So they're neighboring angles. Okay, so let's start with a polygon, and it doesn't matter what kind of polygon you draw. I'm going to choose one with, I'm going to do a pentagon, 5 sides. Okay, so we've already talked about where the interior angles are, but the question becomes, where are the exterior angles? I think I got the right tool here. Let's see how this works out. Okay, so what I'm going to do is I'm going to take one of these sides and I'm going to extend it. Doesn't matter how far I extend it, but I'm just using a ray to extend one side. Now on the inside of my polygon, here, I have an interior angle. If I look at the angle adjacent to that, here, it is now on the outside or the exterior of that polygon. So that angle is referred to as an exterior angle. Now I would do that at every vertex, extending a side. So here I'm going to start there and go this way. And now I've created another exterior angle here. And I can do that again at any of these vertices. Never mind those funny little red dots that pop up. That's just the way this program works. Like so. And I can see that because this polygon had 5 interior angles, it will also have 5 exterior angles. So the exterior angles are the angles outside the polygon. And here again, they can be all the same measure, but they don't have to be. So to show that they are different, I'm marking them all in different ways. But ultimately, 5 interior angles and 5 exterior angles, and we'll talk at a later date what the relationship is between like a pair here. What should be true of an interior and its own or corresponding exterior. And we'll talk about that a little later when we get into some more things about angles. All right, so the exterior angles theorem for polygons, one of the easiest theorems ever. The sum of the measures, not that anything we've done today has been too terribly difficult, I hope. The sum of the measures of the exterior angles of a polygon is 360 degrees. Notice there's no formula there. Simply the sum is 360. Never anything different. So for a quadrilateral, the sum of the 4 exterior angles is 360. In a pentagon, like what I had drawn up above, the sum of those 5 exterior angles is 360. For a hexagon, the sum of the 6 exterior angles would be 360. 10 sides, the exterior angles have a sum of, you guessed it, 360 degrees. Doesn't matter how many sides the polygon has, the sum of the measures of the exterior angles is always 360 degrees. Now, there's one of two things that can happen here. In a problem, it can ask you, what is the sum of the measures of the exterior angles of a fill in the blank? Quadrilateral, hexagon, octagon, etc. And you would write, when it asks for the sum, 360. And I see that here in number 1 below. What is the sum of the measures of the exterior angles of a regular pentagon? Sum. It's asking for the sum. I know it's 360. Sum of the exteriors is always 360. Another type of question might ask you specifically about a regular polygon. And note we have this funny looking little sentence here. If a polygon is a regular polygon, remember what that means. All the angles inside are congruent or equal. Then the measure of each exterior angle will be the same. In other words, they're going to be equal. So if it has 5 interior angles that are all equal, then it will have 5 exterior angles, each of which are equal to each other. If it has 7 interior angles, a regular polygon will have 7 exterior angles that are all equal. So in number 1, what is the sum of the measures of the exterior angles? I just zinged right past that, didn't I? What is the sum of the measures of the exterior angles of a regular pentagon? The sum. So when I'm asked for the sum of the exterior angles, it's 360 degrees. Number 2, what is the sum of the measures of the exterior angles of a hexagon? 360 degrees. So if I see the word sum and I see the word exterior, I know it's 360. If I see interior, then I have to go back to the Polygon interior angles theorem. 3, what is the measure of each of the exterior angles of a regular decagon? I can only find the measure of each exterior angle if I know the polygon is regular. If it's not regular, then they could be any numbers. They might all be different. Some of them might be the same. But when the polygon is regular, I know they all have to have the same value. So what we know here, we know the sum has to be 360 degrees. Here we're working with a decagon, so n must be 10. So I want to find the measure of each exterior angle. I simply take 360 divided by 10. And we get 36 degrees. So each exterior angle of a regular decagon. Can't find the measure of each angle unless you know the polygon is regular. What is the measure of each of the exterior angles of a regular dodecagon? So there again, each angle, I have to know it's regular. In this case, dodeca, remember we looked at that yesterday. Do meaning 2 like dos, deca meaning 10. So here in this case, n is 12. Dodeca. 2 and 10 make 12. Okay, so we know the sum of the measures of the exterior angles is 360. I know n is 12. So I take 360 divided by 12. And that tells me the measure of each of those exterior angles is 30 degrees. Okay, so that takes care of our interior and exterior angles of a polygon notes. The only other thing that you need to do is the assignment, which is taken care of in class.